Welcome to part 4 of chapter 14. Today we're going to continue our talk on chemical kinetics. We are going to look at collision theory, which is this idea that molecules need to collide with each other in order to cause a reaction. And then we're going to start to look at reaction mechanisms today. So collision theory. The idea is that molecules need to collide in order to react, which should make sense, right? If they don't bump into each other, then they're not going to react. But the thing is that not all molecules that crash into each other will cause a reaction. Some of them will just kind of bump into each other and go on their merry way. And so why do not all of them react? Well, two reasons. The first one is that our collisions need to have enough energy to produce the reaction. If, these molecules don't have very much energy, they're just going to kind of bump into each other and leave. So they need to have enough energy to cause this reaction to go. So there's this energy that's called the activation energy, which is the energy needed to, activate the reaction. So they need to have either the same amount or more than that activation energy. They can have more, they can't have less, right? If they have less than the activation energy, the reaction just won't happen. The other thing that they need to have is they need to be oriented correctly. If your molecule is facing the wrong way to cause this new bond to form, then it won't react, right? There's only these specific sites on the molecule that can cause this reaction. And it's really easy to think about this if you're, from a biology standpoint, right? You're looking for those active sites in order to cause the reaction. We're looking at much smaller molecules typically in chemistry, but they still need to, bump into the right side of the molecule in order to cause this reaction to go. So they need to have enough energy and they need to be oriented correctly in order to produce the reaction. If they're not facing the right way, we can't form our new bonds. Okay, so looking at this first one, like I said, they need to have enough energy to overcome that energy barrier, right? They need to overcome that activation energy. If they don't, then they just, will bump into each other and leave. So here, these are, see, they look really exciting. These are our effective collisions, right? They have lots of energy. They're crashing into each other. The reaction happens, okay? This one here, right? Look at, they're just kind of bumping into each other. They're not very excited. They don't have very much energy and they just kind of leave. Okay, so we need to have effective collisions, really energetic collisions. And again, they need to have enough energy to meet that minimum activation energy. And then when they do form, when they do collide with enough energy, they can cause the formation of this activated complex. And we'll look at that in just a minute. So again, like if we're looking at this reaction here, hydrogen reacts with oxygen to produce water. Okay, so if your hydrogen and your oxygen molecules just kind of casually bump into each other, they may not have enough energy to make this reaction go. There's always some kind of energy barrier to reactions. And again, that energy barrier is called the activation energy. That's the amount of energy needed to convert the reactants into this activated complex, okay? You may have heard of it before as a transition state. It goes by both names. So activated complex, transition state, totally the same thing, but it's this high energy species that has partially formed bonds, okay? So it's when, the bonds between these hydrogens are starting to break, the bond between the oxygen is starting to break, and it's starting to form new bonds, right, between the hydrogen and the oxygen. So that's what's happening up here. So the transition state, or the activated complex, that is what's happening at the top here. Okay, so the activation energy is the energy needed to go from the reactants all the way to the top of the hump, okay, all the way up to the transition state. And so the activation energy is often abbreviated E subscript A, the energy of activation. Okay, the activated complex is always super high in energy because it has these partial bonds, right? It's partially, these bonds are partially broken, some are partially formed, and it's really, really unstable. And it doesn't hang around very long. Like really, really short, like you couldn't even measure it, right? You can't like blink your eye that fast. And it's really unstable, just happens for a second because it's super high in energy with the partial bonds. Okay, so again, this is our energy of the reactants, the energy to get to the top of the hump, that's our activation energy. Up here, this is our activated complex or our transition state, and then the energy of the products will always be on the right. So here's an example. So this is the isomerization of methyl isonitrile. So this is methyl isonitrile over here, okay? So the methyl group, that's that CH3, and the CN is the nitrile, okay? When we think about this in terms of formal charges, and you should have learned about formal charges back in Chem 1. So there's this lone pair on this end that's not being shown. But if we think about formal charges, in methyl isonitrile, nitrogen has a +1 formal charge and carbon has a -1 formal charge. If you don't remember how to calculate formal charges, I would look it up. You can also ask me and I will walk you through it. But this is something you should know from Chem 1. If we look at the formal charges of acetonitrile on this side, now carbon does not have a formal charge and nitrogen does not have a formal charge. And if you remember your formal charge rules, right, we want formal charges of 0. So that means that acetonitrile is much more stable than methyl isonitrile. So if we have methyl isonitrile over time, it will rearrange. Okay, and what happens is that the bond starts to weaken between the carbon and the nitrogen. And when it weakens, then that carbon-nitrogen group, it will rotate, and then it will form this new bond between the two carbons. Okay, so in order for this whole reaction to occur, we need to break a carbon-nitrogen bond, and then we're going to make a new carbon-carbon bond. Okay, so this is what it would look like. So here's our, energy of our reactants right here. And then again, we need some amount of energy to start to break that carbon-nitrogen bond. Okay, so we need to put in energy. And the energy that we put in, that's that activation energy. So we're going to put in energy to cause that carbon-nitrogen bond to weaken, and that will cause that, that nitrile group to rotate. Okay, and so this is the transition state. See these dots? Those are the partial bonds there. So it's started to let go of the nitrogen and it's moving over to make a bond with the carbon. Okay. After that happens, right, that activated complex, that transition state, after that fully rotates, it's going to release a bunch of energy and it's going to go to the products. Okay. This we didn't see before. So I'm going to point this out, this delta H of the reaction. Okay, that's we sometimes call it the heat of the reaction. You'll also see it written as delta E because there's no work being done. So delta E and delta H are going to be essentially the same in this case. But it's always going to be the difference in energy between the reactants and the products. Okay, so here's the reactants, here's the products, and the difference between them, that's the delta H of the reaction. Here, because the reactants are higher in energy than the products, this is showing an exothermic reaction. This is going to be a negative delta H. Okay, and I have a slide on this, so I will go through it again slowly. But what I wanted to draw your attention here is that this activated complex has partial bonds that you can see, and the activation energy is always going to be from the reactants up to the top of the activated complex. Okay, let's get a little bit more into endothermic and exothermic reactions. So this one looks different than this last one, right? Here we had the reactants above the products, and I said that this was exothermic, which it is. In an endothermic reaction, the energy of the reactants will be below the products because over time, energy is being absorbed. Okay, so again, the difference between the reactants and the products, that will be this delta H value, often called the heat of the reaction. Okay, so if it's got a positive delta H value, that means it is endothermic. The reaction has absorbed energy. Okay, endothermic reactions are typically going to have a very large activation energy. And if you think about this in terms of the lab, for an endothermic reaction, most times we're going to stick this on the hot plate, or we're going to stick it on a Bunsen burner, right? We're going to heat up our reaction in some way, because endothermic reactions typically either don't happen at room temperature or they happen really, really slowly. So we're going to input a bunch of energy to either cause the reaction to go at all or to make it go a little more quickly. Okay, so like I said, typically a very large activation energy for endothermic reactions. But if I asked you to tell whether this was an endothermic or exothermic reaction, you can always tell because the energy of the reactants is below the products, meaning that energy has been absorbed. So exothermic reactions are exactly the opposite. The energy of the reactants will be above the products, which means that over time, energy has been released. So these are going to have a negative delta H value. Okay. Most times our exothermic reactions are going to have a smaller activation energy because they're not trying to absorb all of this energy. Okay, so they're going to have, a much smaller hump here. Most reactions that we do in lab are exothermic reactions because they're what's called thermodynamically favorable, and we will get into that a little bit later in this course. Okay, but most reactions we're going to look at are going to be exothermic reactions. Endothermic reactions are a little less common. Okay, so here is an example. This is a nucleophilic substitution mechanism. This would be what you would look at in organic, but the reason I'm including it is because you can see the transition state here. So we start off with methyl bromide, okay, so that's this guy, and we have a base, we have a hydroxide. And over time, what's going to happen is this hydroxide is going to kick out the bromine, okay, so the hydroxide is going to add on, and the bromine will leave. In the middle though, right, in the transition state, in the very middle, we have where carbon is still partially holding on to the bromine, but it's partially starting to form this bond to the oxygen. Okay, that is a very high energy species. And so it's not going to hang around all that long, and it's going to be, gone in an instant. So again, just looking at this, the activation energy, I know it's hard to see, but the activation energy is always going to be from the reactants to the top of the activated complex, right? Up to the top of that transition state. This says forward, okay? This is the energy of the forward reaction. So assuming the reaction is going this way. If you look, this arrow, I know it's a little bit hard to read, but this says reverse. So if the reaction was going this way, in which we were adding the bromine on, in that case, if we were looking at a reverse reaction, okay, that is going to be the energy right now. These are the reactants up to the top of the transition state. Okay, so sometimes Alex will ask you, I think there's a couple problems on the lecture worksheet that ask about the energy of the reverse reaction. So you're going to go backwards. Assume these are the reactants, go to the top of the transition state. Okay, and that changes this. Normally, if we were going forward, right, we're losing energy. That would be an exothermic reaction. The reverse reaction, though, would be gaining energy. So that would be an endothermic reaction. Either way, though, the value of the delta H would be the same because it's always the difference between the reactants and the products. But we would switch the sign. Remember, for an exothermic reaction, we have a negative delta H, and for an endothermic reaction, we have a positive delta H. Okay, so if we are increasing the temperature, that means all of our molecules are moving faster and they are moving more energetically. Okay, so if we had this T1, right, this is a cold temperature, that's why it's in blue, our average kinetic energy, is going to be, let's say, here. And at a hotter temperature, T2, that's in red, our average kinetic energy would be there. Right? As we increase the temperature, we are going to increase the average kinetic energy. And if we were saying that, this is the activation energy of our reaction, right? As we increase our average kinetic energy, a greater fraction of molecules are going to meet this minimum energy requirement. So as we increase temperature, we increase the number of molecules that are able to make it over that hump, right? That are able to make the reaction go. Therefore, if we have more molecules that can react, this is going to increase the reaction rate. Okay, the reaction will happen faster because if you think about it in terms of concentration, right, we're essentially increasing the concentration of molecules with that amount of energy. Okay, so increasing the temperature increases the reaction rate. Therefore, the rate constant is temperature dependent, right? Because at higher temperatures, the reaction will happen faster. Okay, because there's enough molecules that can make it over this hump. So just a little bit on effective collisions. Let's say we had this reaction where we have NaCl is reacting with itself and is producing nitrogen monoxide and chlorine gas. The molecules have to be facing the right way in order to cause those old bonds to break and the new bonds to form, right? If you think about that transition state where, some of the molecule or some of the bonds are being broken at the same time that some of the bonds are being formed, we need to have that happening, okay? They have to be broken and formed kind of at the same time. So what's happening here is that these chlorines are going to end up together, okay? So if the reaction looked like this, well, the chlorines are really far apart. Okay, that's an ineffective collision because we need the chlorines to start to bond together before they can really leave the nitrogen monoxide. This doesn't work either because, again, chlorines are still too far apart. So that's not going to be an effective collision, right? Like here, this would be if we wanted our oxygens to bond together. This would cause an oxygen to bond to the chlorine. The only way that we can get the chlorines to bond to each other is if it crashes into each other with the chlorines facing each other. Then the chlorines can start to form the bond and it can start to break these bonds here, okay, between the oxygen and the chlorine. That's the only way that this reaction will happen. Okay, so the more effective collisions that we can have, the faster the reaction rate. We are actually going to look at catalysts in the next lecture, and catalysts help because some of the catalysts, depending on the type of catalyst, can hold your reaction molecules in place so that they force this to happen. Okay, like you could have something hold on to these so that the chlorines have to react together. That's one of the types of catalysts that can happen. So the catalyst can increase the number of effective collisions that happen. Okay, but again, in order to have an effective collision, we need to have our molecules facing the right way. Okay, on to our next topic. We're going to talk about reaction mechanisms. We're going to start talking about it this time, and then we'll continue talking more about reaction mechanisms in the next lecture. So typically, when we write a chemical equation that represents a chemical reaction, we're usually writing the overall reaction. Not the series of little individual steps that happen as the reaction goes. Usually a reaction isn't just like this plus this makes this. That's not normally how it happens. Normally it's A plus B makes C, and then C reacts with D to make E, and then E reacts with another molecule of A to make F, right? There's this whole series of reactions that happen. We will usually write just the overall reaction. A plus B made F, or whatever the case may be. Okay, so when we talk about a reaction mechanism, that reaction mechanism breaks down the reaction into its elementary steps. Okay, and if we add up all of those little elementary steps, they're going to give the overall balanced equation for the reaction. You can kind of think about it like Hess's law when we were looking at that in Chem 1, where we would add up a bunch of reactions and cancel things out to make sure we got this overall reaction. It's the same kind of thought process, right? Those elementary reactions have to add up to the overall reaction. If we know the rate law of the overall reaction, that can tell us the sequence of reactions, or it can help us really understand the sequence of reactions in the mechanism, because the mechanism has to agree with the rate law. Okay, and this will make more sense after the next lecture. Okay, but the rate law is always going to be based on whichever elementary step happens the slowest. Okay, so looking at the rate law of the reaction can tell us a lot about the reaction itself in these elementary steps. So here's an example. So we have a reaction that's written above, and this is a two-step mechanism. In the first one, we are going to have hydrogen reacting with ICl, right? We're going to make, hydrochloric acid and HI. Okay, and then our hydrogen iodide is going to react with another ICl, and we're going to get hydrochloric acid and iodine. Okay, so this is our overall reaction. This is telling us, what we started with and then what we ended with, but it doesn't say what happened in the middle. Our mechanism tells us, okay, well, the first thing that happened is I used this stuff, right? These match, right? Our starting materials match. But in between, I made this. And then I took this guy and I reacted it with another one of these. And then I made this, right? And this matches our products, okay? So these are called our elementary steps. Okay, this is our overall reaction, and these are our elementary steps. So the elementary steps can't be broken down into simpler steps, right? These elementary steps are as basic as it gets. They're showing exactly what happened, what reacted with what in what order, okay? It's going to show all the molecules that actually interact. There's no other hidden steps that aren't happening, okay? So when we write these mechanisms, there's things that come up that are called intermediates, okay? And so intermediates are things that are going to be formed during the course of a reaction and then used up in a later step. So they're not going to show up ever in our overall reaction. So this is our overall reaction. We would never have an intermediate in an overall reaction. So it's going to be something that's formed in one step and then used up in the next, or used up in a later step. Okay, so if we look in this first reaction, we are producing hydrogen iodide. Okay, but then in the next step, it gets used up. Okay, and if we are adding these reactants together, right, these will cancel out. And so it's like it never happened, right? It doesn't show up in the overall step, but it's something that's kind of produced and then used along the way. Okay, so since it's being produced and then used along the way, they are called intermediates. They don't show up in the overall reaction, but there's something that happens during the course of the overall reaction. Okay, they're really important, right? They allow your reaction to go, but they don't stick around long enough. They get used up. Okay, so I want you to do an example and identify the intermediates in this reaction. So this is our overall reaction, right? We're having hydrogen reacting with nitrogen monoxide to produce nitrogen gas and water vapor. Here is our elementary steps. So the first step and then the second step, okay? So if we look at step 1 and then we look at step 2, and then again, this is going to be our overall reaction here. I want you to look at what, gets produced in step 1, but gets used up in step 2. Therefore, it doesn't show up in our overall reaction. So go ahead and pause so that you can think about that, unless you've already got it, but pause and then come back when you're ready to see the answer. Okay, so again, we're looking for what's going to get canceled out, what gets produced in the first step but gets used up in the second step. So if we're looking at what gets produced in the first step, those are these, right? Okay, those are our products for the first step and then our reactants for the second step. So we're looking for something to match. So if you'll notice dinitrogen monoxide ends up in both of those places. So when we look at the overall reaction, these get canceled out and they don't show up anywhere in this overall reaction. Everything else gets added down, right? Here's our 1, 2 hydrogens that end up here, our 2 nitrogen monoxides. We have our nitrogen gas, and then our 1, 2 waters that end up getting added together. Our dinitrogen monoxide is nowhere to be found. It got produced in step 1, used up in step 2. Therefore, dinitrogen monoxide is our intermediate. All right, one last little topic for today is if you hear about this term molecularity. Okay, and molecularity is just how many reactant particles are in this elementary step. Okay, so if we have something that's unimolecular, that's just going to have one particle. Maybe that one particle falls apart, right? It decomposes. That would be where we have just one thing that's reacting. Bimolecular steps involve two particles. This is probably more common. It can be two of the same particle, like it could be two oxygen gases reacting, or two of the same thing, or it can be two totally different things, but it just needs to be two of something. And then termolecular would be three different molecules reacting. That may happen in like an overall reaction, but it's actually really common in an elementary step. Typically, I would say mostly you get two things that are reacting together to make something else. So here's kind of our looking at this. If we look at our elementary step in this first one, we have, A is making products. So there's just one thing here. That means it is unimolecular, and our rate would be K times A. Since these are elementary steps, we can write the rate law using the coefficients from our equation. Okay, we can't do this with overall reactions, right? That's why we were having to use our data to figure out the order of the reaction. We needed to look, okay, if I double A and the rate doubles, that means it's first order, right? Or we can plot things with the integrated rate law and figure out all that out. But for an elementary step, we can use the coefficients from our balanced chemical reaction to write our rate law. So for this elementary step, rate equals K times A, because there's literally just one A sitting here. In the next one, we have, it's bimolecular, right? A plus A. So bimolecular, there's two things reacting, and our rate is Ka squared, because literally there are two A's, right? The next one, we have A plus B reacting. Again, bimolecular, and our rate law would be rate times K equal, A and B, because we have A and B, okay? If we have something that's termolecular, again, these are all really rare, but if we have A and A and A, right, three A's, that would be A cubed. A and B, we would have A squared B, or they could all be different, right? A, B, and C, and it would be A, B, C. But for these elementary rate laws, we can use the reactants to write our rate law, which is super helpful. So let's look at another one. You can think of each of these elementary steps like their own little reactions, their own little activation energies, their own little rate laws. And this will be really important when we start to look more at mechanisms in the next lecture. So if they each are their own little reaction with their own little activation energy and own little rate law, right, we can write the rate laws for each of these elementary steps, but only elementary steps, from their coefficients. And so we're going to use the coefficients as their exponents. Okay. Again, you cannot do this for an overall reaction. The rate law for an overall reaction must be determined experimentally. You can't go doing this, right, using the coefficients as the exponents for overall reactions, only if it says elementary steps, or if it tells you this is the reaction mechanism. Okay. So if we look at this first step here, that means, our rate is going to be our concentration of hydrogen times our concentration of ICl, right? So we have hydrogen, ICl. And our second one, we have, HI reacting with ICl. So we have HI reacting with ICl, okay? You see now that our K values, our rate constants, now have numbers that go with them. Okay, this is telling you this is the rate constant for the first elementary step. This is the rate constant for the second elementary step. Again, we're thinking about each one of these steps as their own little reactions with their own little activation energies and their own little rate laws, so they have their own little rate constants because they are going to have their own rate. Okay, so that's the key bit there. Again, do not do this for overall steps. Just for elementary steps, you can use our reactants in our rate law. And that's it for today. Next time we are going to talk more about reaction mechanisms, and then we are going to wrap up the chapter by talking about catalysts. Okay. As always, go work on these problems in that lecture worksheet and make sure you are solid on this stuff before moving forward. If you ever have any questions, please send them my way so I can help you. Remember, I became a chemistry professor because I like to talk about chemistry and I like to help you out. If you don't have any questions though, keep working hard and I will talk to you all next time.